so much, Fred. Colleagues, it's a real pleasure to be with you all today. I want to acknowledge before I start that I have some very old friends in the audience, some people I've known since I was quite young, and I'd like to say thank you for joining us here tonight. It's lovely to have you here, and I really have appreciated your support over many years. What I want to talk to you about tonight is some work that I've been pursuing now for a reasonable amount of time. But to do that, I need to step back a little bit and perhaps give you an introduction to quantum physics. Quantum is a word that we hear a lot at the moment. That people talk about it quite substantially. We spoke about it in the introduction. Quantum can be scary. It doesn't have to be scary, but it's good to have some sort of working idea of what quantum is. And for those of you who are experts, I apologize. This isn't going to be quite right, but it's going to be close. And I will say, I really missed a trick. I forgot we were at a golf course, and I started with tennis balls, so that's on me. We all understand energy, or think we do. And energy, kinetic energy, is the thing that happens when we throw a ball. And with a tennis ball, you can throw it at some speed, and that speed equals an energy. And if we're not constrained, we can throw that ball at whatever speed we like. There's no sort of limitations placed on how fast or how fast we can throw at any particular point in time. And I might draw a graph that looks something like this. I'll say, for some energy, am I allowed to throw the ball at that energy? And in an unconstrained system, the answer is generally yes, you can do that. The real fun parts start to happen when we start to put constraints around things. We start to limit where and how we can throw that ball. And so let's say I'm in a stairwell and there's some windows. There's only a particular set of values for which I can throw the ball, only particular sets of energies that are now allowed. And I start to quantize the energy of the system I'm working with. And so there is a lot of energies now that are not allowed. We can't live there. And if we try and do that, we're prevented from doing so. And we go from having a situation where all the energies are allowed to starting to have quantized sets of energies that we can work within. And this is fundamentally what it means to be a quantum system. The quantization doesn't come from constraints necessarily from a ball going through a window, but it comes from constraints about the environment of small things. I might have an electron. That electron lives in some place, and if it's constrained, then the energies that it's allowed to have become limited. They become quantized, and that quantization is where quantum effects emerge from. The types of quantum effects I'm going to talk about for the next little while are around a thing called electron spin. So electrons, the fundamental particles that make our world work, have a property called spin. That property can be quantized. It can point up or down like a top, except tops can't really point down. And in the systems we're trying to engineer for quantum technologies, there's only two allowed states. They can really only point up or down. I just want to make sure that everyone in the audience can hear me. Is everyone okay back there? Not very well. I'll try to, if I speak like this, is that better? Excellent, good, let me do that. The quantum systems we're really going to talk about tonight really come in only two states, and we're going to call them up and down. That's just generally what we do as physicists. And the power comes from the fact that we're able to, through applying different sorts of techniques, control those quantum states. And we generally do that by applying something to them. Often, and that allows us to drive in a really predictable way between different quantum states. And the things we're applying are usually things like light, or microwaves, or electric fields, or some other sort of perturbator. And that is pretty much all we need to know about quantum systems for the rest of my talk. They're things where we've designed a system to be constrained, there's a number of fixed levels, and we can control how we operate between them. I made it sound pretty easy, but actually that whole let's constrain something is a really challenging problem, and people are spending an awful lot of time and money trying to solve that challenge. Some colleagues of mine at the University of New South Wales have a company called Dirac, and that company is trying to constrain electrons in semiconductors by applying these really quite complex metallic structures, applying different voltages to them to really try to squeeze those electrons down to little patches. And by squeezing them down, they're applying those constraints that lead to quantized energy levels. This is what people usually think about at the moment when they think about quantum computers or quantum systems. Really complex engineered things that often have to live in a dilution fridge, which is something that makes it very cold. And that's what the thing on the left here is. And those dilution fridges have to live in very large pieces of infrastructure to make sure that they have enough cooling power and electricity to operate. And the bottom picture there is the proposed site for a company called PsiQuantum that you may remember the Australian government invested $1 billion in a few years back to operate a plant up in Queensland. And that's sort of the scale of what we're looking at to run a quantum computer. But my proposition tonight, and then the thing that drives my work, is that quantum behaviors can actually be found in many places. And there are natural systems where quantum behaviors naturally occur that we should be exploiting much more. And that's in molecules. So here's a very boring molecule called pentacene. And apologies to any chemists in the audience. I am not a chemist, so this is going to scare you a little bit how I talk about it, but that's all right. If I take a pentacene and I shine light on that pentacene, I can generate an excitation. We'll call it an electron, although it's not quite an electron, that might look something like this. And so it's a very well-defined, very well-constrained electron on a molecule. And that has all the same sorts of properties that those engineered systems people are trying to make have. And so what's driven my work over the last sort of decade is, can we take molecular systems that exist in nature and do the same sorts of things with them that we do with these much more engineered quantum systems that many people are working on? So why molecules and why quantum? The question we need to answer effectively is, what do we want for a good quantum technology? And I'll talk a little bit about why we care about quantum technologies a little bit further down the track. But there are some things we want for good quantum technologies. We really do want that well-defined discrete energy levels. And molecules give us to that in a really nice way. Every pentacene molecule is identical to every other pentacene molecule. There's not manufacturing errors. There's no problem with my lithography machine that means there's a slight variation in the voltage. You get what you get. Chemists can argue with me later about that, but that's all right. We need to have quantum properties, things like coherence and superposition, and I don't have enough time to really get into exactly what those are, but they're really important properties for us. And molecules can give us that because we're able to really well isolate them from their environment. And we're also able to start to tune their properties by the wealth of skills that we've built up through the whole chemical engineering profession over many, many decades. And that's going to come back to be a really important part of what I'm getting at tonight. And importantly, we need some way to measure them. So a quantum system's only useful in a technology if there's some way to both modify it, to control it, but also to measure the outcome of that. And molecules are really nice for that because they're often optically active. You can shine light on them and they'll emit light back, and the light that comes back from them really does depend on the nature of the quantum states within them. They can also be made into devices. My phone, for example, has an organic light emitting diode as the display element. And what that is an organic molecular layer that I apply a voltage to, and it makes light come out. And I'll talk for quite a bit of time at the end of this talk about that process. And now don't get scared, but this is where all of that comes to fruition. This is an example of a molecular system where we demonstrate coherent control of quantum states. What you'll see here are, let's see if I can do this actually. This is that pentacene molecule. That pentacene molecule has been deposited on some substrate. Here it's just a piece of a different sort of semiconductor. We shine light, here it's a laser, onto that film of molecules, and we have a really solid understanding of what its energy structure looks like. And by figuring out how to play around within that energy structure, we can really start to drive coherent oscillations of our quantum system. We can demonstrate quantum coherence. And that's what this oscillating signal is here and here. This is the signature of coherent effects in these quantum systems. And the really outstanding thing about this system is that this is happening at room temperature. Now, a lot of the costs that goes into and challenges that go into other quantum technologies are that because it's hard to make things very small, the payoff for not making them small enough is they have to be really cold. And a lot of the infrastructure that I showed you around that PsiQuantum building is all about cooling things down as much as possible. It's actually quite a challenge to make something that cold. It takes a lot of energy, it takes a lot of space. That somewhat comes for free in molecules because they're already so small, and the energy scales we're talking about mean that we don't have to be quite as cold in terms of temperature. And in fact, they can come up to room temperature. So that's demonstrating that we can control them. It's demonstrating that we can read them out. But actually the thing that makes quantum systems powerful is when they start to interact with each other. This is a picture from Vivid a few years back, and I really like it because it really fits into my talk. So I just put it in there, somewhat gratuitously, but there we go. This is probably the better picture though. Chemical engineering is a really mature profession. There are so many tools available to us in the chemical engineering world that we've not really thought about applying to quantum systems before because it's a different domain. If we're starting to use chemicals, molecules, as quantum systems, and starting to think about how we make them interact with each other, then those chemical engineering tools really start to become powerful. So let's take pentacene, in this case tetracene, which is similar to pentacene, and say, well, let's say we have two of them. We want to start to make them talk to each other, to interact, to become more powerful. How do we join them up in a way that allows us to do that? And this is one way we might join them up. The beauty, though, of chemistry is that there's an almost unimaginable number of ways we might think about joining these two things together. So here is a collection of different bridges that we can put between these two molecules to link them up. And they have different properties, they have different geometries, they have different distances and size scales. There really is a lot of room for us to start to engineer the quantum properties of the system in a much simpler way than we might have to do in a solid state device. Here's an example of the geometry. So if I take these different bridges and apply them to those two molecules, I can end up with something that's very flat all the way through to something that's very, very bent. And that geometry has a really significant impact on the quantum properties of the system I'm looking at. So here's an example. This is what an excitation on one of these states might look like. When I couple them, it becomes much more distributed. It turns out that this acts as though it were two separate quantum states, and you can have a spin up on one side and a spin down on another side. And we know how they're interacting with each other in a very precise way. And that's really valuable for us because it allows us to start to then think about logic. How do we do logic type applications now with our molecular systems that are showing these quantum effects? For those of you who are from a computer science background, I've tried to map how we might use light and excitations on these coupled molecules to really be analogous to an AND gate in a traditional quantum logic sense. There are ways to excite different parts of the molecules at different times. There are ways for us to read them out in different ways that allow us to implement like quite traditional logic applications on these molecules. That's really exciting for us, and it's really helping us to point in the direction we want to go around quantum systems. So what can we use molecular quantum technologies for? What can they do? The first is things like molecular quantum bits and quantum information. So there are ways for us to think about doing the same sorts of computing effects or computing applications that they're doing with these much more complex systems with molecules. Now, we have different challenges than they do. So our challenge is coupling much larger systems. Their challenge is coupling smaller systems. Our challenge is how do we hold our chemicals? Their challenge is how do they get them close enough to each other? There's payoffs and different benefits, but it's nice to have options. The next is in quantum sensing. So one of the challenges you'll often hear when people talk about quantum systems is that they have to be really isolated from their environment, that they get perturbed very easily, that a small electrical noise or small voltage fluctuation really leads to decoherence quite quickly, and that breaks the quantum information process we're trying to use. You can flip that on its head and say that's actually a really significant benefit of quantum systems if you're thinking about them as sensors. They are extraordinarily sensitive to their environment. They really do couple to specific things in very, very unique ways. And quantum sensing, using quantum systems to sense, is a really significant application at the moment. It's also a lot easier, and I'm going to spend the rest of the talk talking about this sort of stuff. The third is hybrid systems, where we use quantum systems with quantum effects to try to enhance non-quantum systems. So one of the projects that I'm working on in collaboration with my colleagues in the School of Photovoltaics and Renewable Energy Engineering is around putting films of some of these quantum materials on top of solar cells to try to modify the spectrum of the sun before it hits the cell to make the energy capture process more efficient. So it turns out that the ability of a silicon cell to extract energy from sunlight is limited because they're very good at turning a specific color of light into energy at 100% efficiency. The sun, unfortunately, has quite a broad range of colors in its spectrum. And if there are ways for us to transform both the higher energy and lower energy photons in that spectrum using these quantum materials, then we might increase the limiting efficiency of solar cells by quite a significant amount. And that's work we're working on at the moment. But for the rest of my next 9 minutes, I'm going to talk a bit about molecular quantum sensing and what that means and how we do it. And so, in fact, we do it using these OLEDs, the things that are in your phone and my phone. It turns out they're a really exciting system for looking at quantum sensing technologies. And this is the sort of thing we might want to build. We might want to have an OLED and might want to be quite small. We might want to apply some sort of control to that OLED, in this case microwaves, and so we want to build microwave antennas at a very small length scale around it. And then we want to measure the current that flows through them, and that's good. We can do that because we can connect them in giant arrays, again, like the ones on your phone. Building these things can be fun, it can also be challenging, but interestingly, it's nowhere near as challenging as building a modern integrated circuit that you might find in your computer or laptop. They are really complex things. These are much less complex than they are. And so there's a lot of steps where we evaporate metals in particular patterns. We apply different layers of our molecules to make the electronic device, and then apply here this gold resonator here, which is the thing we use to apply microwaves to it. But ultimately what we end up is a reasonably simple system, which is an OLED that we can apply microwaves to in a really controlled way, and that we can measure either the light coming out or the current going through it. And by changing the frequency of the microwaves, or by changing the external magnetic field that we're trying to measure, we can see big changes in the current that goes through that device. And here I'm showing a spectra. So the position of this peak here is related to the frequency, which we're able to measure really well. Actually, we're quite good at doing that with clocks. And it's also related to the external magnetic field. So the magnetic field that sensor is feeling. And it's able to do this over a very broad range of magnetic fields, from well below the Earth's magnetic field up to quite high magnetic fields. And the really nice thing is it's able to do that on very small length scales. So I can put a microscope on top of my OLED. I can look at it with a resolution of a couple of 100 nanometers, and I can use each of those spots I'm looking at as a local magnetic field sensor. And so what I'm showing here on the bottom left is a map of the magnetic field, where each of those pixels represents about 900 nanometers spatially. And so the gradient you see there is from a magnet that's some distance away from it. And there's a real lot of applications if one can start to measure magnetic fields with high precision. There are applications in electronics, which is perhaps not the most interesting one. There are applications in defense. There are a lot of times when one might want to try to identify a thing that's moving and perturbing a magnetic field in places you can't see. An example of that might be a big chunky metal thing moving underneath water. And so given the interest in submarines in around Australia at this point in time, that's an application I think people might be interested in. There's also a lot of biomedical applications for magnetic fields. One of the challenges, for example, in remote healthcare is that whilst it's easy to talk to a doctor online, it's often quite challenging to have medical instrumentation near everybody, particularly in remote areas. And if you could think about turning the screen of a mobile phone into a quantum sensor that could allow you to do things like measure the magnetic field from your heart, say, or the electrical activity in your brain, then there might be really interesting ways for us to improve healthcare going into the future. The other thing we can do is think about making these things really small. So there's a limit on how finely we can look at things. It's called the Rayleigh limit, and it's to do with the wavelength of light and how big our eyes are and all these, and how big the sensing element is. But it turns out sometimes that doesn't matter. Sometimes I can look at something that looks quite big, but because I know that the thing that's emitting the light is very, very small, then I can scan that small thing around and really map out very small variations in magnetic fields, even though the resolution of the thing I'm using to do that is quite large. And one can then make arrays of very small things that are smaller than the Rayleigh limit and scan those around. And there's really fun applications in that sort of technology around things like how do we characterize nanoscale electronic devices? How do we look at defects in modern computer chips? Or how do we do anti-counterfeiting is another really interesting application of this sort of work. So that's sort of the technology and the ideas. Now, the real challenge that often we face in this sort of area is it's all well and good to do that sort of work in a lab. I can demonstrate it quite well in a lab setting, but getting it out into a product that's available commercially can be a real challenge. And so often what we have to do is work out a pipeline to get a lab demo into a product. And the way that we're going about doing that is through a spin-out company that we're calling Ubiquity. It's a bit of a stretch, I appreciate, but that's all right. Which stands for Ubiquitous Quantum Technologies. We want to make quantum technologies that are small enough, cheap enough, and operate at room temperature so that they can be used in many, many more applications than perhaps traditional quantum technologies could be if they're stuck in a fridge or need cooling. And so at the moment we're sort of in this spin out, we're working towards moving from a lab-based system all the way through to field deployable prototypes that we can put out on particular testing systems to do that. And this is an interesting challenge for people who come out of a discovery research world. There's an interesting observation I have around academia at the moment, that the expectation on academics to drive technology spin-outs is a really interesting one, given that often they're people we hire because they're very good at doing fundamental research, they're good teachers, they manage research labs, and then we add this whole other part to their life, which is now go and be an entrepreneur, have a startup and spin a technology out in a way that's commercially viable. I think that's hard, and I think there's room for us to think about different ways to achieve those sorts of outcomes across the sector. But that's probably not the talk I was here to give tonight. And the last thing in my last minute and a half is to say, all of these technologies really excite me. All of the ideas are things that I think are really interesting and intellectually stimulating. But actually, everything that I've talked about tonight is a consequence of having people who, with the right education, the right skills, and the right resources available to them, to discover new things and to drive that technology pathway. And given the Teachers Guild of New South Wales is a sponsor tonight, I wanted to say that strong fundamentals in STEM, comfort working across disciplines, and really understanding problem solving at different length scales are the sorts of core skills that people coming into the world where this sort of work is critical will need. There's also a need for people to be able to collaborate between physicists, chemists, electrical engineers, product designers, but also in places where perhaps not as obvious. Electricians, plumbers. It turns out plumbers are super critical for quantum technologies. And that's perhaps a surprise to a lot of people who don't work in the space. Designers, software engineers, user interface folks, but also accountants and finance types and people in a whole range of supporting roles around that technology development. And so perhaps the message I want to leave you with is not this is a great technology, and I'm happy to talk about that for a long time, but it's that quantum is not a niche. It's not a thing that's restricted to people with PhDs in physics. It's a thing that plumbers of the future, electricians of the future, designers of the future could really do with having a working knowledge of and understanding how their world interacts with this world that feels esoteric from the outside, but is actually designing and building the future that we're going to live in. Thank you very much, and I'm really looking forward to hearing the next three speeches.